In this video we'll learn Euclid's division lemma, see algebraically why it preserves common divisors, and then use the algorithm to find the HCF of two numbers step by step. Euclid's division lemma says that for any integers, a and b with b greater than 0, you can write a equals bq plus r, where q is the integer quotient and r is the remainder, with r greater than or equal to 0 and r less than b. Practically, that is just division. A divided by b gives quotient q and remainder r. We'll use that repeatedly. Here's the crucial algebra. We can rearrange a equals bq plus r to get r equals a minus bq. Let's assume that d is some number that divides both a and b. That means, given two integers a and b, a equals dA and b equals dB. Substitute and you get r equals dA minus q dB, or r equals d times a minus qb. So d divides r. In short, every common divisor of a and b must also divide r. This means that the HCF of a and b equals the HCF of b and r, so we can replace a and b with b and r, and repeat. That's Euclid's algorithm. Because the remainder r is strictly smaller than the divisor b at each step, the numbers shrink at each step and the process cannot continue forever. Eventually the remainder becomes 0, and when that happens, the last non-zero divisor is the HCF. That's Euclid's algorithm in one sentence. Let's put this into practice. We'll find the HCF of 455 and 42 using this. Step 1. Divide 455 by 42. The quotient is 10 and remainder 35. So 455 equals 42 times 10 plus 35. The HCF of 455 and 42 equals the HCF of 42 and 35. That's why we move to the next pair, 42 and 35. Next, dividing 42 by 35, we get a quotient of 1 and remainder 7. So 42 equals 35 times 1 plus 7. Again, any common divisor of 42 and 35 divides 7. Thus, the HCF of 42 and 35 equals the HCF of 35 and 7. We've reduced the pair to 35 and 7. Now divide 35 by 7, quotient 5, remainder 0. Since the remainder is 0, the algorithm terminates and the last non-zero divisor, 7, is the HCF. As a sanity check, both 455 and 42 divide evenly by 7, giving integers 65 and 6. That confirms our result. The same logic applies for any pair of integers. Repeated application of the lemma reduces the problem, and the last divisor is the HCF. To recap, a equals bq plus r, where a and b are two integers. Observe that any common divisor of a and b divides r, and so the HCF of a and b equals the HCF of b and r. Repeat these steps until the remainder is 0. The last non-zero divisor is the HCF.